by 80 meters, that one set traces equinoxes, solstices, more accurate than Stonehenge. It's 5,000 years older than Stonehenge. It is the oldest astronomical experiment in the world, an hour and a half from here. But there's like 3 people who knew that. And it's not negative on anyone. That's the point. Is there's so many things that are happening. There's so much knowledge that are built upon, 60,000 years ago, 11,000 years ago to today, that is what we're doing. That's what we're talking about. Now, so I have a question. We're in the school, so you have to be clear. Is this taken from space or not? So if you think yes, raise your hand. All right. If you think no, raise your hand. Good. All right. So the no's win. That's fine. That's good. You are correct. Now, space. Does anyone know where space starts? Yeah. 100? Is it 100 kilometers? Is that what you said? That is correct. Well done. Here, you want a duck? Oh, I can't catch it. Flying, here, catch. Flying duck. I'll throw it at you. Sorry. In astronomy, that would have won a Nobel Prize. So it's 100 kilometers. And the reason it starts at 100 kilometers is not scientific. It's just because it's a nice number. No, that's the real answer. There is no reason why space doesn't start at a height. If you're at 99 kilometers, if you're at 101 kilometers, it's the same thing. It's just there's this international rule that says that space has to start somewhere. And in fact, the US military recognizes 80 kilometers. And so if you reach 80 kilometers, you get your space wings. And so Virgin Galactic, who's had their first couple flights, who may set up operation in South Australia as well, they have pilots reach 80 kilometers and they got their space wings. Of course, that's not the legally recognized height, so Jeff Bezos and Blue Origin had a Twitter jab. So in this day and age, people fight on Twitter because they're billionaires having their own space companies. And it's kind of an amazing statement. And so the reason I want to say this is there's this issue that we have of space law, and that is the law of space. What governs the things above us? How do we deal with what's above us? Because there's a lot to it. And space law is this thing that is really holding the world back. And I'll do an experiment here, right? I'll take you fine. So you can be Australia, right? Now you can be a satellite company in Australia, right? Now you're New Zealand. It's a good area, right? And you're a rocket company in New Zealand, right? With me so far? So the Australian satellites will go on top of the New Zealand rocket. This happens like once a month. Sorry? You want to shoot them into space on a giant rocket? Oh, okay. We'll leave that for later. The law of space is different. You can be a space pirate if you want, so you can do whatever you want. So, alright, so the Australian satellite New Zealand rocket, but you're going to launch from French Guiana. Because you don't like Australia or New Zealand. It's a better place. With me so far? Again, it's really convoluted. This happens like every 6 months. Now, the Australian satellite of the New Zealand rocket is going to launch from French Guiana. It's going to crash into the Russian satellite. You're Russia. Who's at fault? Now, obviously, if you're American, you say it's Russia. But, New Zealand? China. So, it's, yeah? Neither. The satellites are colliding in space. Yeah?
Did the New Zealanders launch the rocket for the Australians?
So the New Zealand's yes, they did. You think it's New Zealand? Yeah? Australia? Those are all reasonable guesses, but no, it's French Guiana. They who touched it last is responsible. That is like, it's like someone wrote this as a joke and they're like, all right, it's stuck. And again, the laws of 1967 are not representative of today, yet that's what governs our space. And so how do we deal with this is a big deal. right? You know how SpaceX, Elon Musk's way of sending money into space? Well, you know how those reusable rockets, which are really great, you know how they land on barges 20 kilometers off the ocean?
International waters.
International waters. They're not legally responsible. They just circumvent the laws if something goes wrong. So all of these things creep up into how do we deal with this. Now, I'm going to show in this video because this was actually taken out on a satellite with a giant balloon. One of the cool things we're able to do now is we're able to build balloons that are about 2 stories tall, and they stay in the air for 6 months at a time, and they're stationary. So they go up and they stay there. And we're mounting these giant telescopes, about a meter size, these telescopes, these balloons rather, and so we can image the entire sky almost like we're in space. And the cool thing is, these balloons, they come back down and land, so we just refill them and we relaunch them. And so it's a way of accessing space reusably and cheaply. Now we do want to get further into space. And the problem is, you know, things like SpaceX, those rockets are great. Current rockets are really inefficient, right? So rockets are essentially giant bombs that we strap people to. And the problem is, you need that energy to escape gravity. That makes sense. But the bigger you make a rocket, the more energy you get. Except you don't, because you add more weight, which adds more gravity. So you have to add more energy, which adds more gravity. So there's a limit to how big you can make a rocket. And so there's 2 ways. 1, we build a lighter fuel source, a lighter engine. Or 2, we launch from somewhere with less gravity. And we're working on both. So, in school, you're taught that there's 3 states of matter: solid, liquid, gas. Well, there's actually a 4th, something we call plasma. Yeah? Good. So how do we make plasma? You just know it exists? How do we make it?
Well, plasma, you take a gas.
Yep.
For example, let's say oxygen in the yellow atoms. Then you send it on the current to it, and you get plasma around the current. If you want that, the plasma effect electricity, so you actually can see the electron.
That's right. So we supercharge a gas. Here's a plasma dunk. Plasma dunk coming through. There's close enough. My boss is accurate to 100 million years and also got a Nobel Prize, so it's fine. So the cool thing is, that's exactly right. So we can take a gas, just supercharge it. Now the benefit of this is we can get a lot of energy. So in camera, we have a chamber that's roughly the size of here, this size, and it's a simulator. It's a space simulator. It simulates the conditions of space. And so when we build something, we can test what it's going to perform like in space. And so here, we have a little ball of plasma that we just ignited. We put that current through it. It's going to grow. It's going to grow. It's going to grow. Keep growing. And it'll stop here and it'll reset. So we had a little fuel source, put charge through it, and it expanded, like propulsion. Now, it might not look like much. It's not a big rocket. But that also weighed 2 grams. So the entire fuel source, it's not tons, it's not hundreds of kilograms, it's just 2 grams. It is the lightest fuel source you can build that is almost purely efficient. Which means that when you build a big rocket and you put it on it, or you put it on a satellite and you just push it and keep pushing, you get really fast, lots of energy for very, very little fuel. Now that's good. Now I said the other part is we're just solving the gravity part, and that's why we're going to the moon. Now right now, there's a project between the US and Russia and Canada, soon to be Europe, most likely soon to be Australia, that's building a space station around the moon. It's called the Gateway. So just as we have the space station that orbits the Earth, that we have astronauts to it, that you can see sometimes at night, that at 400 kilometers is closer than Sydney, we're building one of these around the moon. So the first 2 parts, here and here, are designed to go up in 2022. They can carry 4 people at a time for 1 to 3 months. So people can hop down to the surface, so people can do experiments around the moon, or so things that can dock on it. Now, people say we didn't go to the moon, and I don't know why. I'm happy to shoot anyone to the moon who really wants to prove otherwise. And the funny thing is, I think it's partly the reason that we often ask, why haven't we gone back to the moon? And so we have to evaluate the question, why did we go to the moon in the first place? And that was because the entire goal was the moon. And so we got there, I was kind of like, what do we do now? So we just built space stations around the Earth instead, right? Space is an expensive game. A lot of people were sad when the US space shuttle was canceled, but it was $1.5 billion per launch. So when you're launching 10 to 30 times a year, you're spending $30 to $100 billion. It's expensive. The moon is even more. And so the reason that we hadn't gone back was the cost. We didn't have a reason. But now we do. Now, and I like showing this picture because one of the things that Apollos 11, 12, and 14 did was left these metal reflector plates on the moon. They're not very big. They're about the size of a table. You can kind of see some footprints to scale. And what these were left with is these metal reflector plates were left so that we could bounce lasers off them. And Australia was one of the first countries to do this. We bounced lasers off that little table, that little plate, and bounced it back to the Earth. And it's told us that the moon is drifting away 4 centimeters a year. That every year, the moon is 4 centimeters further. And consequently, while minimal, that means the day changes. So in fact, scientifically, every Monday is longer than the previous one. And that's something that we know. And in fact, if you go far enough back in time, if you're around the Earth 4 billion years ago, the entire day is only 12 hours long. And in fact, it's a direct consequence of how life formed on the Earth and how the moon has come and drifted away. Now, I said we have a reason to go back to the moon now. That is because there's a lot of ice. Now, when we go outside tonight and we see those dark areas, those dark gray areas are what we call Mare, dark lava. The moon has lava. And so as that lava came, it also brought a lot of water and ice with it. And this is great, because water and ice happen to be made of 2 things, hydrogen and oxygen. Rocket fuel happens to be made of 2 things, hydrogen and oxygen. You can convert ice into rocket fuel. And because the moon has very little gravity, you can take off on the moon and go to Mars. Now, a lot of people are talking about these colonizations of Mars. Here we go. So, now, there's a lot of similarities between Mars and Australia, especially Western Australia. In the sense that it is a desert, we can see evidence of water flows there. You know, you can see probably here's some dry river beds. We think that Mars was a lot like Earth billions of years ago. Now, here, I'll do a survey and then I'll make Eloise also answer and I'll answer. So, and you can answer this any way you want. Who believes in aliens? So, now obviously, firstly, when we say aliens, we generally mean life, right? So, we're like, elephants are like bacteria, plants, animals, dogs. So, when we often say aliens, we use this as a catch-all term for life. So the second question, who thinks humans at some point will go to Mars? Now the tricky question, what do you think will happen first? We discover aliens, or there's a human on Mars? If you think aliens first, raise your hand. If you think Mars first, raise your hand. Eloise, why don't you answer?
Are the people coming back from Mars? I would say we'll find aliens first. The people are returning from Mars. The people who are not returning from Mars are becoming Mars.
Fair enough. So I think that's a fair assessment, yeah?
Would there be any chance that there'd be bacteria in the ice?
In the ice. So, get in here. So, I think life is common. I mean, Eloise, do you kind of agree with that? Yeah. I think most scientists, most astronomers and us would agree that life, that catch-all term, is common. You know, what Eloise will show you, planets are common, stars are common, galaxies are common. There's a lot of stuff out there. As I often say, I don't worry about when we find life or aliens. I worry if the answer to, is there life somewhere else? And it's just us. Because I don't know if we know what that means or how to handle that answer. Now, I think aliens exist. I'm debatable about whether humans will get to Mars. I think we will send a human body to Mars. Whether that survived the trip or not is a different story. And I, by far, think we will discover aliens before humans are on Mars as early as 2022. Now, there's water on Mars. There's evidence from the flows. We see underneath the surface. In fact, using radar, it's been shown that about 1.5 kilometers underneath the ocean, there's these pockets of salty water right now underneath Mars. So if you think that Mars has all this water and we know life traces water, it's a good chance that there's life there. And in 2020, there's now 3 rovers, at least 2 of which are being sent to Mars, that will be able to detect some sort of life thing. And they're landing in what we believe are old oceans. So I think land launches in 2020, it arrives sometime late 2020, early 21. You give it a year of operations, that gives it 2022. It's probably found evidence of something that could be living on Mars. Now, I don't think it's green eyes and these weird beings or Marvin the Martian style. I would be cool if it was, to be honest, but it's going to be something really small and disappointing. But there are other places in the solar system that are better. And some of these are actually these moons, as we call them. And so this is a real video. Here's Jupiter. And these are 2 of the largest moons, Io and Europa, going in front of Jupiter. So here's the Great Red Spot. You can see it with a telescope. It's not up tonight. Well, it's up in the early morning if you're an early riser. And these moons, and as we'll go into the next clip, Titan, the largest moon of Saturn, are really interesting places in our solar system. Because, so here's Titan. Again, this is an actual photo, a time lapse. You can actually see the ring, how thin the rings are. You can see even the shadows of the rings. Now, the reason we get excited about these places, especially Titan, is when we look underneath the surface, we see rivers and lakes. So this is the moon, Saturn. Now, it's water and ammonia, so we don't necessarily drink it, but we can't drink salt water. And in fact, if you add up how much water there is on these moons, there's more water on them than Earth. And that's not even counting some of the other moons that are potentially great. There are so many great places to look for life in our solar system, it's not even fun. And right now, missions are being built and designed to hopefully land on these moons to explore what's underneath the surface. And it will probably find something as well. I mean, if you think about it, in the next decade, we are very likely to have that answer to the question of can life exist somewhere else. And this isn't science fiction, this isn't make-believe, this is just what people are working on. And there's even better things. So, Hayabusa 2, this is probably one of the coolest missions ever that someone legitimately got paid to do. And so this is run by the Japanese Space Agency with France, Germany, and Australia. And about late October, it landed these little Roomba-like probes, these little Roomba-like vacuum cleaners on the surface of this asteroid. And then, about almost a month ago now, this happened. So the probe came down, and so this is an actual video of what it did. So we have the probe, and what we'll see here is about now, it'll start heading to the surface of this asteroid. Then as it reaches the surface, it's going to release a 10-kilogram charge of C4 and shoot a bullet and blow a hole into the asteroid. And then a whole bunch of rocks are going to fly up, and it's going to try and scoop it. So we're about to the surface right about now. You'll see it repel off the surface. Here's a hole in the asteroid. Here's all the rock shooting up. So this trying to collect as much rock as possible. It is then going to come back and land in South Australia in November 2020. So not only are we able to probe these things and rightfully blow them off if we want to, but we can actually start sampling it. Some of the first results of this will be released at 4:30 in the morning tomorrow. And this is kind of amazing that we're able to do these sorts of things. Right? That's not amazing, but look, I said Mars, and then I don't know if humans will survive the trip going to Mars, just like Matt Damon. And I think the Martian highlighted a real problem, and that is when we think of space, it's a lonely place. So, this is an actual photo of the first untethered spacewalk. So he was built in like a NASA jetpack and floated around. And so when you think of space, you think it's cold, right? Space is cold. It's not actually always cold, it's also hot, right? Once you're outside the Earth's atmosphere, if you're on one side of the Earth, away from the sun, it's minus 150 degrees. 45 minutes later, you're in front of the sun, it's 150 degrees. So you go from boiling to freezing, boiling to freezing, boiling to freezing. Human bodies don't like that. There's very little gravity, there's very little atmosphere, there's a lot of radiation. In fact, it creates a laundry list of health problems. And this is actually something that people are trying to grapple with, the health effects of space travel. Does anyone know what animal, this is my favorite question. It's good for any trivia. Does anyone know what animal's been the most in space?
Monkey?
Not really. What? What, dog? No, the Russians love choosing some. Yeah.
Fly.
Sorry?
Fly.
No. Yeah. So we have set some tardigrades, but it's actually not number one. Yeah. No, chimps haven't been that many. Yeah. Rats, not as many as you think. Ladybirds? You're actually getting closer. It's not a land animal. Spiders? No, that's Michael Bay's next film. Ants? No. Birds? No. Closer? No. Frogs? No. Jellyfish. NASA's bred 60,000 jellyfish in space. Now, obviously the question is why. And look, they weren't like floating around, they were mutating. So, when jellyfish reproduce, they reproduce a lot. They reproduce quickly. And when they reproduce, little crystals form in their tentacles, or in the base. And so in microgravity, those crystals form differently. So NASA bred thousands and thousands and thousands of generations of jellyfish. And then they brought them back down to Earth, and they couldn't swim. They form differently. In fact, there's a very widely popular theory, and you'll understand why it can't be tested, is that because the atmosphere and third the pressure, or third the gravity of Mars, if you're born on Mars, you'll structurally be formed differently. And so if you came back to the Earth, you'd just be crushed. Right? Now, obviously, we don't want to test that experiment. But this highlights the problem. Like, how do we deal with these health effects? There's a radiation issue, right? I mean, just simply, if we're to look at radiation, this is like a chart of radiation. Here's X-rays. This is how much you should get every 5 years, but you get it in 6 months on the space station. This is the career radiation limit a U.S. government employee is allowed to get, and that's how much you get to Mars. Due to workplace health safety laws, no U.S. government employee, i.e. NASA, is allowed to go to Mars because they see the radiation limits. How do we deal with this? And NASA is trying to deal with this. They put 2 people in space. These twins, well, one twin. They actually chose an American and a Russian, and he's an identical twin. And they're actually able to see, are they genetically different? Do they age differently? And the answer is yes. By being in space longer, you change. And we don't know how to deal with that. So when it takes 940 days to do a trip to Mars, mustacheless one is the year one. Both have actually been into space. Scott has been in there longer here for the year. Mark was in there shorter time. So they are able to test not only is it just an exposure to space, but is it length of exposure? And the answer appears to be yes. Psychologically, people have been testing this as well, right? How do we deal with the loneliness of it, right? So if you're an astronaut on the space station, you keep the time of your country. So if you're American, you wake up at Houston time, go to sleep at Houston time, call home at Houston time. Russia, Moscow time, Europe, Berlin time. On Mars, it's not possible. It's a 20 to 30 minute delay. There's no hope of escape. You just see this little blue dot, that's your home. Even if you wanted to go home, it would take at least 6 months. It's a very lonely place. And you get stuck with a bunch of people you may not like. And this is a real thing. So this is an experiment that's been done. And so psychologists in Canberra designed part of this where willingly 5 or 6 people signed up to be locked in this bubble for 500 days. Because I agree. Can you psychologically survive being locked and trapped in this lonely, distant place with no hope? And look, you can even see that there's things. See all this fresh fruit and vegetables? That's because the psychological impacts of those are actually important. So how do we deal with this? Well, we can take the human out of the equation and build satellites. So these are all the satellites around the Earth. There's a lot, about 4,500. Every week, roughly 20 new ones are put in orbit. The current record is 161 satellites launched on one rocket. Most of them aren't that big. They're about the size of what we call loaves of bread. That's the entire satellite. And as these satellites go up, they eventually die. And the problem is this, right? In 2009, we saw the first crash between 2 satellites. There's an Iridium satellite here, and then there's uncontrolled Russian satellite. So in this case, the answer is Russia. And before impact, they're here. After impact, they created 10,000 pieces of debris. And the thing we worry about is not necessarily George Clooney dying, though in the movie Gravity he does become space junk, which is kind of nice, is that they do real damage. So on the left here, this is a picture of bulletproof glass from the space shuttle Atlantis. And this hole, about 5 centimeters deep, and it's caused by a flake of paint. Because when you're traveling 40,000 kilometers an hour, you don't have to be very big to do a lot of damage. So in fact, when an astronaut drops a screwdriver or spanner, and there literally is a screwdriver and spanner currently orbiting the Earth at 40,000 kilometers an hour, you do not have to be very big to do this damage. And of course, when things crash into each other, they break apart, they float around, they crash into more things, they break apart, crash into more things. There's an actual real worry, what we call Kessler syndrome, and that is there's this chain reaction upon which so many things are floating around, everything's crashing into each other, and you cannot escape. And in fact, the entire low Earth orbit, where most of our satellites go, would be entirely polluted, and you cannot launch anything into space. Current models say it's going to happen in 2035. It's not an abstract issue. And so what we have in Canberra, and we're building one in Western Australia, and now another one in Long Reach, Queensland, is this giant laser. So it's a real photo, you can see it on the mountain, and we can find an object that's a centimeter wide at 3,000 kilometers above the Earth. The second part of what we're doing is not only trying to find this stuff to limit where it is, but the new laser, which is coming online in July, will be able to de-orbit the debris. So if you imagine it's like water going down a drain, slowly spiraling around, slowly falling towards the Earth. We use a laser and shoot at it so it pushes it straight up, so then gravity pulls it straight back down and burns in the Earth's atmosphere. Because what goes up, must come down. And everything that goes up will eventually come down. Even the space station will come crashing into the Earth at some point. And that's a very scary thought because it's as big as a football pitch.
It's already happened.
What?
It's already happened.
That was the Chinese one, yeah.
Skylab.
And Skylab. The International Space Station is much bigger than those, let me tell you. And, you know, the Skylab issue highlighted a real thing. There was no plan for when Skylab came back down. And so it just crashed over to Western Australia, and luckily no one got hurt. And so now, all large pieces of spacecraft are designed to land in the Southern Pacific Ocean. But that's not a good solution, and we need a better one. Now, that's just a taste of what's going on around us. There's obviously a lot more to it, and I'll let Eloise talk about it.
Okay, so yeah, a bit of a change of pace. So I wanted to tell you a bit about the work that I'm doing for my PhD. So I'm a PhD student at ANU. Originally, I'm from Victoria. I'm from Yale. That's like an hour and a half east of Yale. That wasn't even like one of my planned jokes. So just really excited because now I have a picture that I can include in this slide about like baking a PhD. Yes, so when you open a recipe book, you can sort of see what's going on there. You have a plan of what you're going to do. So that's what we're going to do here. We're going to start off by gathering our ingredients, getting everything we need together. Then we'll make a star. That takes a while, but we'll get there. Then we'll make our planets, because you can't really have a solar system without planets. Then you just have a star that's just by itself. That's kind of weird. And then we get to do our solar system. So, yeah. We're going to need some stuff to make our solar system. We're going to need gas. We're going to need lots and lots of gas. In fact, we're going to need 10 million cups of gas. That's 10 with 30 zeros after it. So that's only for one star, so yields one star. Then we're going to put all our gas. We need to make planets. So we're going to need some dust. Sorry. Yeah. So we need dust. So that's and a million tablespoons of dust. So a bit more than you have floating around in the pantry or under your couch. And yeah, that's just to build us one solar system, not heaps. We need a cold, dense place. So in our cosmic kitchen, we're kind of hanging out in like a giant meat freezer. So it's really, really cold. It's minus 263 degrees Celsius. So think of how hot your oven goes and then make it go backwards. It's very cold. And it's hundreds of light years across. So this image here is of a region that is going to 4 stars, and it is hundreds of light years across. And that's what helps make hundreds of stars. We don't need something back to each and one. It's kind of like the whole batch of cookies versus like making one. And then finally, we need gravity. And you can think of gravity as kind of like the thermomix of your cosmic kitchen. Does everything. Helps you do everything. Right? So now we've got all that stuff together, we can start cooking. So to that, we're going to get a little bit closer, take a close look at this region here. And yeah. So having a close look at where we've got the box. So this is where we're forming stars this year. And in fact, we've got stars forming in these little nodules, like these little like, pointy bits at the edges. So that's where the stars are currently forming. So to make our star, we're going to gather all our ingredients together in our whole dense place, and we're going to collapse it down. So we're smushing it, combining it, so you know when you get a mixture and you start kneading it, that's kind of what's happening here. Combining it all together. This is where we use our gravity, so instead of us combining it all together, gravity's doing that. Gravity's pulling everything in. Pulling everything in, everything's getting nice and becoming a nice little blobby sphere, hopefully. And that's going to take you around 10,000 years. So you know how recipes sometimes tell you, go and watch an episode of a TV show or something while it's cooking. That's a lot of TV. Yeah, so taking another close look, so this region. Sorry, I'm not using Twitter. It's like getting upset. So yeah, you can see these little bits here are where the stars are currently forming in this class. So step 2. Okay. Once we've got enough gas, we'll have a baby star. So it's, like I said, we've got our dough. long oven timer. And yeah, so this is what we're going to make our planets out of. So to make a planet, we need some ingredients, but we don't need that much. We just need stuff that we already had left over, so dust and gas that's left over from making our star. This is good, you're using up all that leftover stuff that you had floating around the kitchen. And it needs to be around a young star, which is good because we just made a young star, so it's already there. Good. Okay. Yeah. So in a disc like this one here, so as I said, you've got a disc of material around the star hanging out in the dust. And you can see here there's like weird dark bits in this disc. So you can think of that as like there could be like a baby planet or something in those gaps, and it's kind of acting like an ice cream scoop. So it's like scooping up material and gobbling it up and getting bigger and bigger, and then so that's how you can form a planet. Yeah. So this is where our planets are going to grow, and these rings here might be signs of planet formation. Because it can be kind of hard to make planets, so we can help them along. And one of the things that might help them is things like this, where there's extra dust. So, you know, if you've got your mixing bowl and stuff gets stuck to the side and you squish it back in and then it gets started again, or you sort of clump things together and bring it together, that's what happens here. So if there's more stuff, you're probably more likely to make a planet. So if you're walking around a room or something, there's not many people, you're not going to run into people that often. But if there's a crowded room like this one and you all get up to leave, you're probably going to bump into people. So that's what happens to the planets here. So because they grow by colliding with each other, you know, if there's lots of stuff in one place, they can get bigger. And so eventually you'll end up with planets, or rocky planets at least, and they might stay small like asteroids, or they can keep growing and get as big as things like Earth, or even bigger. Now, to put the icing on our cake, we can take our rocky planet, take it out, further out in the solar system, shove it right out there, past what we call the ice line. So that's where water, or carbon dioxide, or ammonia, and all those sorts of things are frozen instead of in a gas phase. So they're solids. That means our rocky planet is sort of bump into them and gobble them up. So it gobbles up the gas and the ice and gets bigger and bigger, and then you end up with something like Jupiter or Neptune. And then, as always happens, in the solar system, we go from our solar system, we clean and clean up. That's not as much fun. But stuff just clears away. It takes around 10 million years. I mean, I know sometimes cleaning up after you've been cooking feels like it takes that long, but it doesn't actually take that long. And the left of the solar system, so that's pretty neat. So yeah, it's a bit of hard work, but you get to enjoy the solar system in the end, and I think it's definitely worth it. And I think our solar system, is worth 10 out of 10.
So I just want to end on a couple last things, and then we'll take time for some questions. Right? You know, and it's really important to show that it takes a long time to build these things. And yet, when we look across the universe, and it's 93 billion light years, or 47.5 billion light years aside, and we see that every star in the night sky that you'll see with your eyes tonight probably has planets around it, multiple planets, and there's probably 300 billion stars in our Milky Way planets, so there's trillions of planets in our galaxy, and there's 2 to 5 trillion, 2 or so trillion galaxies in the universe. There's a lot of stuff out there. And we're now just on the beginning of trying to see that edge. Now, when we go outside tonight, these are small telescopes, and they're similar to our size and eyes, so they just see a little bit bigger than what we did. But Galileo used the exact same size, very similar to see the 4 moons of Jupiter. When we go use the telescopes outside, you'll see much fainter light. But if your telescope was this size, the size we'll use tonight, if that was your eye, you would see the same thing. Telescopes are just like buckets. So if we want to see fainter light, we need a bigger bucket. And that's what this is. It's a new telescope we're building in Chile. It's called the Giant Magellan Telescope. So you can see here's a person to scale. So it's 25 meters across. So to put this in perspective, here's a person. Here's the Hubble Space Telescope, which is 2.4 meters across. Here's the new space telescope called the James Webb Space Telescope, which will be launched at some point, which is 6.5 meters across. And this is what we're building. So it is big, and that's good. Now it is here on the Earth, which means we have that thing called the atmosphere, which is annoying. I mean, it's good because we need to breathe, but it's bad for astronomy. I also don't like the moon because it pollutes the sky, but I can't destroy the moon, at least I'm told. So I don't. But one of the things that we're doing is, so stars twinkle because of turbulence in the sky. So the same reason your airplane shakes is the same reason a star twinkles in the sky. And we can correct for this. So this telescope's building these lasers. And so we'll have a laser that'll go into the sky. Go up here, it'll twinkle, it'll move around, no wobble. And then because we know exactly where that star, it's a laser, should be, what it looks like, we can build it so that these mirrors change shape. And in fact, they can change shape at the same rate the atmosphere moves in less than a millisecond. So if your atmosphere is wobbling around, the mirror wobbles around. So you can actually take out the effects of the atmosphere. So the telescope would be 100 times more powerful than the Hubble Space Telescope, with 10 times better images. So put this to scale. This is what we'd see on the ground normally, from a normal telescope on the ground. This is what Hubble would see at the same area. This is the new James Webb Space Telescope. This is what we'll see. We're going from that to that. So it will be the biggest, most resolved thing in the world because we want to see these very first galaxies. Because we know when the Hubble Space Telescope points at empty parts of space, it sees this. Every single dot here, -3, here, here, and up there, yeah, are galaxies. That smudge, that smudge, that smudge, that bigger smudge. There's 22,000 galaxies in a single image alone. 22,000 galaxies with hundreds of billions of stars. And yet, when we think about what's in the universe, it's only a small fraction of everything. There's actually a lot more stuff than this. In fact, if we add it up, only 5% of the universe is in stuff that we can see. 95% of it is in stuff that we can't. And this 95%, dark matter, dark energy, they're not related. It's not like equals mc squared, we're just not creative people. Is that both of these were in part discovered by Australia. Right? Australia helped discover 95% of the universe. And that's really what it is. And when we think of things like what dark energy, what I work on, we know that it's causing the universe to grow. And as it gets bigger, it is likely that in fact the universe will rip itself apart. That is one of the options. Now it's not anything anytime soon, but the cool thing is, if you take a universe and you rip it apart, you rip or separate space and time. And you release all of the energy of the universe, which then releases all of the energy of the universe. It's kind of like a Big Bang, which in fact might create a new universe. And in fact, it could be that our universe is a previous universe that is ripped. And in fact, there's multiple universes out there, each with multiple galaxies, each with multiple stars, each with multiple planets. So that chart I just showed you is just representative of one of these universal bubbles. So it just keeps going on and on and on. Not only is there no end, there is not even a thought of how there is an end. We don't even know where to think of where the end is because we don't even think that far back. And, Eloise and I just gave you a taste of really what's going on. There's a lot more than we've even covered. And I think this is the cool thing, is this is what's happening. These things, from finding Tatooines and how to build a solar system just to blowing up asteroids because it was fun, is all in a day's work. And the great thing is, it's never been a better time to do these things. you know, for all the young people out there, or the older people who want to switch jobs and blow up asteroids and become Bruce Willis. You can do that, right? You know, I just like to highlight, in the Gold Coast, right now there's a group called Gilmore Space Technologies. This is like a legitimate family-run rocket company. And it's a husband and wife, and now their kids work for it, and they're building a rocket, and they're almost ready to go. It should be ready to go in a few years' time. Like, that's kind of strange, and that's really cool. And that is what is going on. And so there's all of these things happening, and it's never really been a better time to be involved in this. And it's only going to keep continuing. It's only going to keep more. And there's only going to be more stuff going on. So what we might do is we'll take time, we'll answer a few questions. We'll go outside and do stargazing after, but you can also ask us questions as we go outside. So does anyone have a burning question that they really need asked? Okay, lots of people. Here.
When is the Americans planning to go to Mars? Is there any official?
Any official? So right now it's in the 2030s. And the reason it's so long is one, humans don't survive the trip. And two, they are having problems with their new rocket, which is called the Space Launch System. So this is kind of the new big rocket that will take people further in the solar system. What's called the Orion capsule, which is the new pod that will carry the people that will sit on top of that rocket, is ready to go and should be tested in like 2 years' time. So that is the official timeline on the US getting to Mars. Russia has a similar agreeable timeline. Private companies that hit that earlier. But a good example is you're going to sit in a room and ask SpaceX, what are you doing about getting people to Mars? Their answer is, we're a transportation company. They don't worry about the cargo, they just get it there. And people are cargo on these missions. So while SpaceX is likely to get to Mars soon, is that people, first will be robots and stuff like that. And if there's someone on that rocket, will they survive? And I don't know. I'm not going to be the one that finds out. Way back. Yeah.
Yeah, if that multiverse theory is true, then you said that if it was created by different universes moving off each other, then it'd be like an origin universe, which they will start moving off each other.
Potentially, and then the question is what created that, and then you just keep going further and further. I mean, and this is kind of the cool thing, is like, there's some ways we don't have a way of tackling this problem, and yet we're able to answer this question, right? Ask this question. And so it's a bit out there, so to speak. I don't have a good answer to
Greg, to get back.
that. Would it be possible to travel beyond space and time and go to another universe? No. And look, it's a good question, because if I were to send you currently in the fastest rocket or the fastest satellite, which is 700,000 kilometers an hour, it's the fastest thing humans have ever built, it would take you 15,000 years to get to the next closest star. So, which is only 4 light years away, not 93 billion light years away. So the good question is, it is almost so insurmountable about how do we get there. I don't even know how to even remotely tackle it. And I'm not, it's a really interesting question, because we want to know what's beyond the universe, what's beyond the beginning. But we just reached this like thing where we can't even begin to try and tackle it. So we need someone to either create a new way of thinking about laws of physics that go around things like Einstein and relativity, or someone that has a lot of energy, or both. Yeah.
Regarding observing gaps, how do you deal with gravitational lensing, and what do you think is causing it?
Gravitational lensing? So, I mean, gravitational lensing, so what the question is about is, if you were to put a light source behind something that has a lot of mass, gravity can actually bend that light. And we see this all the time. When we look at clumps of galaxies, we can actually see beams of light curve through space. So gravitational lensing we kind of know what it is. It's gravity can actually bend light, and that's because light is similar to everything else, and we can change it. And a similar technique is actually used to find planets.
Yeah, I was going to say, there's a technique that we use to find exoplanets where if the star and the planet move in front of the background star, you can actually see the light bending around the star and the planet. So you can actually use that to detect exoplanets. So we actually have purposes for using gravitational lensing. It's actually very helpful.
In fact, one of the very first planets was discovered using gravitational microlensing by accident searching for dark matter in Australia. Yeah. So the question is, if the moon drifting away, won't it drift further as it gets further away? So the answer is kind of in short, yes, right? As gravitational weakens, it will slowly drift away, right? The good thing is it takes such a long time, you're not really around to measure it. You know, even if you allow it to go for about 10,000 years, it only adds about a second and a half to our day. So it takes a really long time for this to happen. So again, it's like Eloise said, luckily everything takes a really long time, so we don't really have to worry about it. But in theory, if you allow it to go for a really long time, it would speed up and speed up and speed up until eventually it would leave the Earth. But probably not before the sun destroys the Earth, I assume. Similar time scales, it's fine. Maybe what we'll do is probably one or two more questions, and again, we're happy to take more outside. Yeah.
Dark matter. Is there any specific word we're looking for?
Ooh, so searching for dark matter.
So I know a couple of the instruments are actually looking for dark matter in our galaxy, and what they're doing is, so in our galaxy, we've got sort of clusters of stars that are sort of quite far away from the middle of our galaxy. And those are globular clusters, they're called. And the thing is, you can look for, so they're kind of, possibly they were like smaller galaxies that have fallen in and stuff like that. So they should have dark matter around them if they were previously like another galaxy. So looking at the light from those and looking at looking at the motions of the stars in those clusters, you can potentially detect the presence of dark matter. You can't see it, but that's one way you can detect it. Also, we can see it in other galaxies by measuring how bright they are, and then also looking at how the stars in the moon. So if you look at how bright they are, you can get a mass based on the matter that you can see. So you will end up with one number. Then if you look at how fast they're moving, you get a different number when you calculate the mass. And it's much bigger. And that's because how fast the stars are moving is also influenced by the dark matter in the galaxy. So that's one of the ways that they first sort of detected dark matter.
And so I was just using my phone to look up another location. So in the North Grampians, in Stallwell, there's the dark matter experiment. So what they do is we think dark matter might be this really big, massive, small particle, smaller than a proton, a neutron. And they're waiting for it, because it's really heavy, and if it travels fast, it has a lot of energy, it goes through the crust. It hopefully can keep going down. So in the Stallwell gold mines, at a kilometer deep, they have these giant tanks of gas, noble gases. Xenon's a popular one. So if a dark matter particle comes and hits the gas, it'll hit one of those atoms, hit an electron off, and it'll spark, and it'll create like this giant neon sign that says, "Hey, dark matter is here. Congratulations." It hasn't happened yet for the building. Want to take one more? Sure, right here. So, I think it's all the time we have. Here's a water bottle while I think of an answer. So, that's a good question. So, the answer is both yes and no, and I don't know, and I can't know. And those aren't the same thing. So, if we go back, if I go back to where my plot of the observable universe is. So, when we say the universe began, or the Big Bang began the universe, it really began space and time. And so when we go back to the beginning, what we see is that there essentially is the creation of everything. Now, I said the universe, I don't know what it is anymore, is 93 billion light years across. So it would take light 93 billion years to get across. So here we go. Now, the universe is only about 13.8 billion years old. And what's actually happening is the universe is growing 68 million kilometers per second. Pretty fast. And because the universe is growing so much, so let's imagine here's the boundary of the universe. Here's the edge, right? And here's light from that edge. Well, the boundary is now moving faster than the light. So when we look backwards, we can't actually see this beginning. So everywhere we look is infinite. So if you look that way, if you look that way, that way, that way, that way, you cannot see an edge. And that's because the universe is so big. Now, the interesting thing about it is if you were to be around 5 or 9 billion years ago, you would look out and see a telescope. You could actually see an edge because the universe was much smaller. And so the cool thing about this is that because our universe has grown for so much, that there's probably things we're missing. Like there very well could be a sign giving you the answer to literally every question, every lotto number, who the next prime minister is tomorrow, everything like that. But because we can't see it, we will never know it. And in fact, if you're to be around, if you're going to hang around for about 2 billion years, and you do this whole thing, and you look up with the big telescopes and do all these experiments, you will understand the universe in a very different way because you'll be seeing different stuff than we are today. So the great thing about studying the universe, it is always, we try to have a complete picture of the universe that we know is always going to be wrong. And it's the sense that when you're trying to understand what the universe is, it's almost trying to understand existence unto itself, and there's almost a limit to it. So in a roundabout way answer, don't know. And that's just because you can't, and that's a very good thing. So when you become older, you can potentially create a new laws of math and physics and a new way of thinking about the universe that can actually do that. And people have done that. Say Einstein or Newton or a bunch of people. So it is very possible, and there are people right now, it's called string theory, trying to figure out a new way to describe the universe so we can answer that very exact question. So maybe in 10 years. Now, one last very eager question in the back.
I have read an article saying that you were a part of an asteroid mining
Project, yeah.
I was wondering how it worked and what we could find out.
Yeah, so asteroids are great. There's a lot of them. They're the leftover bits that we're cooking. And they're also giant chunks of metal. One asteroid, let's take a 4.5 kilometer asteroid, it could have about 100 million tons of nickel. That's about 100 years worth of mining global production. Another can have 300 years worth of platinum. So the reason we think about asteroid mining is it's kind of like the new gold rush. There's 20 private companies designed or ready to mine asteroids. More are built every day. The entire space economy of Luxembourg is built around this. There's now a yearly conference on asteroid mining. Because how do we extract things in space is a global thing. What we are doing is not only figuring out how to do it, because it's actually kind of easy. We just blow them up. But there's real consequences here. So let's say I take 100, 300 years worth of platinum. What's going to happen to the global platinum market? It will crash, right? But we all have gold on us, right? Most of us. Not in rings, phones, circuitry, because it's a good conductor. That has gold here. Platinum is 1,000 times better as a conductor than gold. So you immediately have a bunch of cheap platinum. You imagine instantaneously boosted electronic power by 1,000 times overnight. Now, nickel. Again, you bring 100 years worth of nickel down, you're going to crash the nickel market. But we all have nickel on us. Lithium and nickel batteries. So if nickel and lithium are so cheap, then renewable battery storage is essentially zero. So there's real tangible productions. There's never been a model of this because we've never had unlimited resources. There are 100,000 at least of these types of asteroids. There is no limit to how much stuff there is. And the worry is, what is the other stuff? What happens when a global superpower, choose your favorite one, decides to perfect asteroid mining? Then they have all the resources they need. So they don't have to import from other countries. They don't have to worry about trade agreements or policy agreements. There's a lot of ramifications. In fact, a year and a half ago, this mission that's bringing stuff back to the middle of Australia in 2020, which, by the way, legally, if something goes wrong because it hits our land, we're the legally responsible ones. The NASA Office for Planetary Protection, this is a real office, it's not shooting down aliens, but it's protecting the planet and all sorts of things, said that our policies for asteroid return sample missions is woefully inadequate and we should all be worried. That's like the official NASA line, is that we should be worried. And it's landing in Australia in a year and a half and no one's done anything about it. And it's because I don't really expect there to be some sort of contaminant or contagion that creates this outbreak. But what if? And so what we're trying to do is to get a whole bunch of these different people who are thinking a lot differently than me, because they're thinking of all these other things to try and solve it, because asteroid mining is going to happen. Because in order to do all this stuff I talked about, you have to extract resources in space. China on January 3rd landed on the far side of the moon to probe the reserves of helium for potential bases. The other person who participated in that mission, by the way, Saudi Arabia. You wonder why, right? Everywhere you look, this is happening, and so this is exactly what we're trying to tackle. So, what we'll do is, I guess if Caroline wants to come up real quick. Thank you everyone for listening. What we'll do is, if you just give us a few minutes, we're going to go straight outside. That way?
Yep.
Sure. I'll let you explain, you know, directions.
The Kindness CWA group has catered for tonight. So I know it's a little bit late, but please take some food home. Down in the atrium, which is the next building that way, there is a massive table of sweet and savoury food.
She created a mooncake.
Yes, there is an awesome mooncake complete with Lego people, star biscuits, things like that. So when I was contacted by Brad to have him visit Kyneton, I was absolutely thrilled. I touched base with Damien from Sacred Heart, and they have let us use the theatre to work together, bring this event to Kyneton. So on behalf of the Macedon Rangers community, I'd like to thank Eloise and Brad and the Australian National Uni and the, what's the name of the telescope?
Oh, Astro 3D, Mintel, yeah. So it just says the telescopes we're using tonight, each school gets one after we're done, so you guys can do your own stargazing in the future.
Yeah. So if you want to go get food, and then what we'll do is we'll go to the telescopes and go right outside, and so you just give us a few minutes to set up. And if you got a gold coin,